Yeah. Yeah, sorry for, I can see the title here is different from what it is in the program. But this is really work on induced polarization. We've been doing this with Gianluca Fiandaca and Anders Vest Christiansen, and then Clara Stekula and Ken Laurie from Geoscience Australia. And Clara was actually supposed to give this presentation, but I will try to do as good as I can. She has been in Aarhus for almost a year, and this is part of what she was working on. So this is my outline for the talk. I'll give you a short introduction, and then I'll talk a little bit about forward modeling and inversion of these airborne IP data, and then I'll show you results from a case study in the Howard region in the northern part of Australia near Darwin. So the motivation here for us to go into this work has been that there's so much talk about induced polarization, but also that it has been a very handheld process to work with these data. And the purpose here was really to come up with something more automatic. So it's not something which is almost an art to work with, but can be done more on a routine basis and also more automatic, so we can run it not only on individual profiles or individual flight lines, but actually can run it in large surveys. So that was kind of the motivation of this. And another thing has been that whenever we look for IP in airborne EM, we surprisingly often find it. That's the, you can say it can both be the good side, because there's a lot of information there, but it also really, it is troublesome. We also start to look for it in ground-based TEM data, and we should stop doing that because we find it when we look for it again. Yeah. There are really two cases, as I see it, of IP parameterization in the AEM data. The first one was what Marco presented this morning, where we are basically trying to figure out what is the polarization of that body in the subsurface, and we use that as a geological descriptor, as he showed in the case from Brazil. And then there is the other case where we really just want to get rid of that effect, so we can see what the underlying resistivity structure is. And what I'm going to present here is more taking the second approach. We want to get rid of that effect so we can see what the real resistivity structure is. Then we can also kind of divide these polarization into, we call them a strong and a weak polarization. A strong polarization is where we have sign changes in the decays. That would be in mineralizations. It could also be in permafrost. We've seen very strong polarizations and sign changes in permafrost. But very, very often, and that's also the dangerous ones, is where we have basically too steep decays. So the decays, and this is what's shown over here, this is the noise level. You can see that above the noise level, we don't have really sign changes. We just have kind of, the signal is subtracted, so we get these over-steepening decays. And they are the one we need to handle because they are present in airborne data. They are, as I said, also in ground-based data. So there are some challenges here. We need sufficient signal-to-noise ratio to do this. And then it's also a challenge for the inversion because we're basically getting 2 or 3 extra parameters in the inversion, so resistivity and these 3, a chartability and a time constant and a C, but there is no extra data in the inversion. And then it is also computationally very demanding because we have a full dispersive model, so we cannot use some of the fast forward routines we normally use for working with airborne data or with TM data. Data processing is also often more handheld compared to normal data processing, and we would definitely like to be able to speed that up so we don't have to spend so much time in front of the computer screen. So the goal of this study here is to come up with a standard processing where we basically room all negative data at the end. And then we want to be able to apply it to a full survey, 2,000 line kilometers in this case here. And we use the MPA model for the model discretization. Marco also talked about that And really the goal is to, in our case here, is to improve the hydrophases input for groundwater models and estimation of subsurface water. So I'm not going to talk at all about MPA, but basically say that it is we're using the cold model to describe the dispersive of the forward response. But then there is a re-parametrization of that called the MPA. Basically, what comes out of that rediscretization is that we basically get it when we look at model resolution, the model parameters basically becomes better determined. And we have shown that extensively in a couple of papers. In this paper here, which is where it was first introduced, that is basically, it better decouples the model parameters, improving the model resolution, but it is, behind the scene, it is just a cold model. But it turns out that this is a better way, a more robust way of inverting the data. So we use that. If you want to know more, these two papers here will be good to look into. Let's see on a model like this what these weak IP responses look like. So it's a relative resistive model with a resistive layer on the top, a little bit more conductive and then more resistive. And we have some, this is the chartability. In this rediscretization, this phi max, and you will see me come back to that several times, is the controlling parameter for how chartable is the layer. And then we'll run through a different scenarios. Basically, we will alter this phi max in the first layer, so replacing this one and vary it in. And just to show you some forward responses, this is the second scenario, and here we're just changing the resistivity of the third layer. And basically, and I'm sorry that this all comes in at the same time, but here is the background response. That is this yellow hatch line. That is without any polarization, and then these curves here basically show the polarization where the lower one here, so this is the noise level, it would correspond to the lowest polarization, and then when we increase it, you can see how it grows up. But in any case, the point here is that we don't have any sign changes above the noise level. So this is one of these cases where we wouldn't see, we would just see it. You can see how much actually the curves are changed. There is a huge difference between the background and then having the polarization. Also when we don't see the sign changes. So this is what we're going for. The next case basically illustrates the same. Here we are changing the polarization in the second layer, and we kind of have the same picture. They spread out nicely here and compared to the background, and in any case we wouldn't see these systematic sign changes. And this is where we change the conductivity and keep the polarization fixed. These changes here is basically due to changes in the conductivity of the second layer. And again, we also see there are some changes. So this polarization is also, it's highly dependent on the conductivity or the resistivity of the layer. So the more resistive the layer, the more clear signature we have on the IP response. That was just to get an understanding of what we're looking at. Yeah, so even small chartabilities alter these decays significantly, and I think that's one of the take-home messages, and that's also why we start to see it so often. So basically, and I'm not going to show this because Clara gave me this figure, and I'm simply not going to try to explain you what it means, but you just have to trust me. If you want to know more, we can have a look at that figure. So basically, she did a number of model sensitivity analysis, and she also did some stochastical modeling on this, because the idea was, or the question was, if we do have sign changes, are we then going to bias if we remove the sign changes, do we then, I mean, maybe we don't have them, right? That's one case, but even if we have them, do we then bias our model estimate after inversion? And the conclusion is that it does not decrease the model resolution significantly. That's a little bit of a soft conclusion because, of course, you're taking out information in the data. But basically, if we just have these over-steepening decays, it's not so bad, actually. We can actually do a lot. And when she ran all these models where she was starting the inversion with perturbations again and again and again, and this is actually what is shown in these plots, which I'm not going to, again, still not going to explain you what actually contains, but she actually ends up with these same model parameters in the inversion. So, so it is an okay approach to take the over-steepening part if this is all we got, and we can actually get close to getting the invert for the polarization. Then let's move to Australia. We are in the northeast part. We are in west of Darwin, so in the very north part. It was a SkyTem 312 survey flown not too long time ago. There is approximately 2,000 line kilometers of data, and it is the purpose of the investigation is a water supply for Darwin, and it's to map water, groundwater for Darwin and the surrounding communities. So Darwin will be up here, and here is an outline of the flight paths. We applied, or we didn't do this in the first time, but this is what we can do now. It went on and on for a long while until we found out how to do this. But we calculate data uncertainties from the raw transients. That's quite important. This is something which has been put into the software within the last year. But that case, we need that good error estimate on the data, and this is coming directly from the raw transients. And then we remove coupled data to any infrastructure, if any, in Australia. There was very little to remove here. There's not a lot of infrastructure, so that's an easy task to do. Then we apply these trapezoid-formed averaging filters, and again, they're very narrow. They're probably very conservative here because there's a lot of signal and a high moment in the system. And then we basically remove negative data and data with a standard deviation of larger than 20%. I'm just gonna I'm gonna go back to misfit. So the object function of our inversion routine and also expressing the data misfit is basically in the simple form. It's basically the difference between the observed and the forward data divided by the standard deviation. That's why this standard deviation is so important. So this is our data misfit, and you also readily see here that if this number here is 1, that means we are fitting our data to the noise level. I just want to keep that in mind. If it's above 1, we are in average fitting worse than or we are not fitting to the noise level, and if it's below 1, we are fitting better than the noise level. It's just because I'm coming back to that. And then we use this parameter-dependent damping. I'm not going to go into details on what that is, but that's actually very crucial that we have that implementation in the inversion, because otherwise the procedure becomes more unstable. These are raw data. You basically see these are the channels, and we are showing, I don't know, 3-4 minutes, and you can basically see this looks like normal noise. There's no particular system in the sign changes, and these are the decays, low moment, high moment, and then we get into the noise level down here. And after processing, it looks like this. So it looks completely like a normal data set, and these are the process data. I'm going to run 2 inversions. One we've just run the resistivity only inversion. It's a 1D LCI scheme, 24 layers, discretized down to 400 meters, and standard vertical and horizontal constraints. And when we run an MPA inversion, I'm going to refer to this as RO, resistivity only, and MPA. And we gave it relatively conservative starting models, and we found out that it was good to add a little bit of a priori constraints on these C and our phi max, just to keep them not wandering off. It stabilizes the inversion. It doesn't really bias what comes out of it, but it's always good to keep a tight leads on parameters like that. This is the data misfit, which is resistivity inversion, and 1 is just in this yellow color here, so we can see we have some stretches here where the misfit is actually quite high. You can see here, so a good part of it is below 1, but there's also an important part above 1. And when we run the MPA inversion, you can see that a lot of these areas, like this one in here, has disappeared, and the residual has gone down. And if we divide the areas into 6 data subsets, this is probably 6 flight days, 1, 2, 4, 5, 6, and we look at the resistivity only residuals, that's the blue ones, you'll see we are in the range of 1.1 to 1.2 in residual, and then we run our MPA, so we include the inversion, our residual goes down to about 0.8. So it means that we are, in average, fitting our data quite significantly better. And if we look at data which were not fitted with a residual better than 1.1, then we can basically see that this is in percentage now. So we can see that that was about 30% not fitted data, and after we included the polarization, we get down to about 10% of the data not fitted well. So there is, we are definitely doing a better job in fitting the data. Then I'll show you a couple of profiles. So this is the resistivity only inversion, and there is an induction log over here. And basically, I think I have maybe, yeah. So let's go to the geology, what it is afterwards. But basically, we have a conductive layer here in the surface, and then a much more resistive layer down here. And that is actually very resistive, you can see down here. If I show the same section where we run the MPA, and now I'm going to put the geology on, we basically see that this is a dolomite aquifer, and we got a weathered clay-rich unit on the top. So, and basically, this is where all the polarization is. You can see how much it changes the resistivity here in this in the dolomite aquifer. So the resistivity goes down, and you can also see how we get the resistivity of the clay unit to go up again. And basically, we have some, this is probably a fracture zone or something like that. You also see here where we don't have this clay layer in the top, we don't see any changes down here. That's very important, right? So it means that the polarization, including these parameters, is actually doing nothing when it's not necessary. That's a good point. And we get much closer to the induction log in this one borehole here. Colors match better. And there's one more, then we can put in the polarization, the phi max, and basically you can see it is, all the polarization is confined in this top clay layer here, and that's what causes, you can say, all our problems in the lower part. Another profile, and I only have two, so again, the same story. We have these high resistivity blobs, and we get a somehow much nicer picture when we include the polarization. Probably these are weak zone, fracture zones, but I don't know enough about the geology to say what it actually is, but it's clearly coming out better here. And then these are the induction logs. Yeah, and the polarization here. I think I'm short in time, so I'm going to jump to my conclusions. These are just maps. They show the same conclusion. Yeah. So what we have been working with in this case here and try to develop is a data processing which is fairly simple, and we use kind of standard approaches. The MPS parameterization decoupled parameters, and we have shown that both theoretically and also in practice in this work here, and it increases the inversion stability. And stability means both when there is polarization in the data, it's accounted for, and when there's not polarization, they don't wander off and do something we don't like because there is very little information about them. And we have also seen that even relatively low chargeabilities causes steep decays. I mean, it changes our decays. Also, when we don't see sign changes above above the noise level. And the decays carries lots of information about the IP parameters. That's one of the take-home messages. And then we have seen here in that the results here shows greatly improved and more consistent resistivity models. Thank you.